We made those kind of inhibitors and we started testing them. And I'm going to make a long story short because what we found out is that our peptide intermediate has activity, but the free boroalanine all by itself was way more active. And we were like, wow, okay, that's not what we expected to find, right? It's like the boroalanine is a really good antibacterial. And so we started thinking, well, how could it be working? Well, we have this alanine branch in the cell wall biosynthesis pathway. We're thinking, well, it's probably acting there somewhere. Well, how do we figure that out? Oh, that's a problem, right? That's not so easy. So our next slide. Oh yeah, so it's got pretty good activity, but it's not great. It's not good enough to go to the clinic, unfortunately. If we had like 8 times lower, if it was 8 times more potent, we'd probably be in Fat City. We'd be, rich and stuff or whatever. All right. Okay, next slide. And so, but we wanted to know how it worked. So what we did is, what we need to do is we need to be able to measure the levels of alanine, of L-alanine, D-alanine, and D-L-D-L in the bacterial cell in the absence and presence of this inhibitor to see which step is it blocking in that pathway. All right. So it's really tricky to resolve enantiomers. So we can always ask the question: why did that chemist cross the road? To get to the other enantiomer, right? Oh, that's a bad one. All right. So there's a man named Murphy invented this reagent called, and he named it appropriately. He named it Murphy's reagent, right? And so what it is you take an old reagent called Sanger's reagent, which is like, old biochemists will know Sanger's reagent. Yeah, that's what everyone uses to tag amines. And it tags amines really well, all right? But he stuck an alanine, an extra alanine on here, so that when it reacted with D-alanine, he ended up with 2 chiral centers. And this center is always L, so this one can be D, or it can be LL, all right? And those are diastereomers now. So enantiomers always act physically identical, except in an achiral environment, all right? But diastereomers can be resolved on just typical HPLC media. So if you shoot like these on an HPLC, they will separate into 2 peaks, one for L and one for D. And then what we did is we made a mass spec method out of this. And I thought about actually spending a lot of time talking about mass spec because it is incredibly powerful technology. I love mass spec. And one of my students just got a really big job at Harvard just after graduation because she's an ace at mass spec. And it's really revolutionizing the life sciences research. But we can see all these intermediates with mass spec very easily in a single run. And we had this impurity. We were wondering, what the heck is that? Well, it turns out it's beta-alanine, which is also in the cells. And then if we isotopically tag it, we can see another peak for the isotopically tagged the alanine. And we also got the Diala from the same experiment. So we extract the bacterial cells, react with Murphy's reagent, we run it on this LCMS method, and we get all this data. And we can see exactly what's going on. So next slide. So when we did this in E. coli, and we use cycloserine, because cycloserine can inhibit either of these 2 enzymes depending on bacteria, but in E. coli it inhibits this alanine racemase. So here's alanine from the bacterial cells, and then here's the D-alanine, L-alanine, here's the D-alanine, and then here's the Diala. So what we see here is for cycloserine, we see a big drop in Diala, which means that cycloserine is inhibiting the enzyme that converts this to this in the bacteria. But when we go over to here, and when this is decreased, then the Diala is going to go down because that's part of the pathway. But we see D-boroalanine is knocking down the Diala. So boroalanine is inhibiting this step here. And this step here is joining 2 peptide fragments together. It has a tetrahedral intermediate too, just the exact opposite of a penicillin binding protein. So the boroalanine, the transition state analog idea for inhibiting something in this pathway worked. It just worked on the wrong end of the other end of the pathway than what we had originally expected. But so anyhow, so that's like, we found this antibacterial agent. It's kind of interesting. It's a very useful probe, but it's not potent enough to make it as an antibacterial, but it was getting pretty close. So we were really encouraged by that. So let's go to the next slide. And how long have I been talking already?
41 minutes.
Okay, all right, thank you.
You're wrapping up.
Yes. Okay, so then what we did is we said, well, if we can see these intermediates, that's really good. So we wanted to get the rest of them. So that's a lot harder because those uridine-linked intermediates are kind of big, kind of gnarly-looking molecules for an organic chemist, you know. But we used our mass spec again, and we can separate these all on a mass spec, and we can see each one individually with mass spec. And I could spend a whole hour talking about mass spec. Let's go to the next slide. And we started using this then to really study this pathway. So we're really interested in dissecting this pathway, because the more we understand about this pathway, the better we can design agents to target it. And so in this experiment here, we're looking at MRSA, and here's all the intermediates on the uridine part of the pathway, and then here's all the amino acids that are kind of auxiliaries to the pathway. And in the absence of any antibiotics, we can see these levels of all these intermediates. And then we can hit it with one antibiotic and then another, and we can measure the levels and look at what's going on. And it's telling us where regulatory steps are in the pathway, because we see things pile up, but then right before them nothing happens, but then something further upstream piles up. This is clearly an example of some regulatory loop there. And so this has been really interesting, and we're doing a lot with that kind of technology. Next slide. And then we can probe the kinetics in the next slide. Okay, so what we want to do though is we want to discover some new agents that have some potential as antibacterial agents. So the classic example of a drug that has to be metabolized to be active again is Prontosil from Domagic, the old example. So next slide. So our idea for screening is we want to screen and we want to find hits. But since a lot of drugs have only been discovered as hits because they were metabolized, we want to make sure we have the metabolites in our screening too. So we take the compounds and we put them into these plates. And we use these kind of plates here. So there's some that have this is a really high density plate, 1500 wells. This is a lower density plate, 96 wells. And I can hand these around, and then we'll have them up in the front if you want to look. And there's even much higher density plates. So this sort of screening now has become big business. There's high throughput screening facilities at every major drug company, and they screen, I mean, they'll do a 1 million compound screen for a target, and then they'll do that like 300 times. They've done that 300 times for bacteria, actually, trying to find new antibacterials, which is a massive effort, billions of dollars. And so our idea was to take a library of compounds plated in a 96 well plate, and to screen those compounds for activity. And then to take the plate and add human microsomes to the plate, which we find from people who come to the lectures and then fall over dead because it takes too long. Sorry, I'm just kidding. And then we metabolize the library compounds, and we generate all the metabolites of the library compounds, and we screen those. And then next slide. And this works. And this is like some of our data. This is 3, so we do everything in duplicate, and you can see the red spots here where we got a hit on the plate and on both replicates of the plate. So that's a good hit. These are our known antibacterial agents, things like tetracycline, vancomycin, etc. And then we have them here as well, because this is like the high density plates. It's kind of a little bit of a story. This is dextromethorphan here, and notice that dextromethorphan is active over here at high concentrations and then disappears after metabolism. But we see a lot of new hits. This is kind of hard to look at. So next slide. So this is where your high school math comes into play. So you have the intersect of two sets, you have the union of two sets, you have all these kind of logical operations on the set. So we have the set from where we didn't metabolize, and then we have the set of results from where we did metabolize. Well, this is both sets merged. This is both sets where it has to be in both sets, all right, to show up as a spot. And this is where these are the hits unique to the unmetabolized plate that disappeared though when you metabolized. And then these are the hits that we only got because we metabolized the plates. So we have all these unique hits from metabolism, and these are likely to be compounds that have never been seen before, because when you buy a library, they know what every compound is. But when you generate the metabolites, it's all new chemistry. So you're taking, it's really got a lot of interesting aspects to it. So next one. And so we got 39 hits from the unmet plate that weren't present after metabolism, 66 common to both, and then 42 of the hits were only present after metabolism. And we're optimizing metabolism conditions, so now we're up to like 60%. We're getting 60% additional hits after metabolism. And then here's two compounds. This compound here is mitomycin, and it's active both before and after metabolism. This compound is porphyromycin, it's inactive unless we metabolize it. And we have a whole list of these on the next page. And so here's a whole bunch of compounds we're pulling out. So these are all different structures of compounds that were active after we metabolized them. And so it's like looking pretty interesting. So we're working on figuring out what the metabolites were. And what we really want to do then, this is where we've done all this with what's called the NCI Diversity Set 5 library. We get it free from the National Cancer Institute. Then the next page, what we're going to do next is we're going to do this to the FDA approved drug library. Any hits we get of an FDA drug, we don't have to worry about all the clinical trial problems that are associated with the drug discovery process. It's like $2.5 billion to develop one drug. $2 billion worth of that is getting it getting through all the pre-development work to getting it to the market. It's really hugely expensive. And so this is that plate map of an FDA. This is one plate from an FDA-approved drug library that we're going to be screening pretty soon, both before and after metabolism. So we're really excited about that. And then the last slide, and we do computational drug screening too. And so we got these hits by running this on a computer. So this took like 2 weeks of computer time on my poor laptop, right? Because I had one program running. So I decided I'm going to get an account at MU, where they have a cluster of 5,600 CPUs. And I submitted a job there like a year ago, and I just watched this thing like just, I mean, it was massive. It was like I had 1,000 CPUs running, at once. And they had somebody running a job called Beavis, right? And so I was like, oh, I'm going to name my job Butthead just because, But I just thought, oh, they're going to kick me off that server if I do that, So, but we got some hits like this, so we need to do more of this. All right, and then the next slide. This is like, okay, so this is not my work. This is really exciting though, and I want to spend a minute on this because this is really imagination capturing. So all these antibiotics, they got them they dug them out of the ground. You think I'm kidding, right? They dug them out of the ground. What they do is they dig up a soil sample and they find new bacteria in there. And the bacteria in the soil are competing with each other constant. For the last 4 billion years, they've